Earth is flat.
You're right.
You look like you're dressed for warmth. Look at those pants.
Yeah, wow. I got up and it was 8 degrees at my place, so I was taking the weather seriously.
I would pay your heating bill. if I were you.
Well, we live in an apartment, and we have other apartments adjoining us. Our heating bill is approximately zero. Because, and we live in a building that has interior
Well, this
hallways.
sounds like a better place.
So
It is a very good
the
place.
hallway is heated at a community expense. And then we have neighbors above, below, on both sides.
Yeah, that all helps.
So we have, of the 6 surfaces of our apartment, 1 is exposed to the weather.
Yeah.
The window.
So that means 8 degrees was
Yeah.
probably warmer than it really
It
was.
was interesting because we
Well,
always told them, look,
I don't know. My thermometer is kind of on the fritz.
always a waiting
The
list.
external
And
unit
it
batteries
was- there
are
definitely wasn't anything.
failing, so I
Exactly.
gotta
So
deal with that.
They finally put their names on 2 of the lists.
But I'm impressed. People,
To the third
this group
place because
gets together, even though every Thursday is.
There.
Commuting is
4
difficult.
cottages, and they wanted a cottage.
So if you can get
So
here,
they
the least
got
we could
into
do is get
the
here.
place
Well,
that
yeah,
ultimately we
it
moved
takes me
to,
an hour
and
from
she was like,
Broomfield. I leave at
"Yeah,
8:15 and I get
me and my brother and I were
into the
like,
building at 9:15.
Don't do it, Mom. You're not happy."
Part of which is walking from
I really
Yes.
wish to go back. and
the
do some of
parking
those.
structure
The
L.
final twist is
Yes.
Are worried about that.
most ambitious and creative work since
She
she
loves
So,
it.
of all the.
Do you have any trouble with finding?
She got a
Oh, yeah.
sad cottage.
No, and
You know, everything is.
Oh, that's great.
They renovated it,
But also,
2-bedroom, they turned, it was a 3-bedroom, they turned it into a 3rd bedroom.
you'd think there'd be a flood.
Someone expanded that, they hosted the,
Has not been a problem.
But anyhow,
and it's
this is how, if you go up, pick it up.
she's got, it's her, one of her cousins lives 2 doors down, moved in recently.
Hello.
Or,
Got 2 elevators.
yeah,
that come down.
exactly. And they have
Yeah.
to meals,
Daniel,
if
Yeah, I
you
walk, so I
don't
just,
wanna go to the dining
I find
room,
that
then
easy.
you call ahead,
historic.
they'll bring the dinner to you.
so far.
Yeah. And everything's
Goes in
close,
off
and
of that.
she's like, I don't know what to do with this video. It's like-
Wow, that's great. She said that?
Yeah.
That's great.
And it is.
Is it well
the
written?
wind's not.
Yeah, yes.
Yeah, but
That's what they do.
And my dad passed away 2 or 3 years after they moved in.
Well, a few days.
Before we got married,
Yeah.
And wasn't
Well,
around. And they
it's more, it takes more
I'm not- I don't know.
Besides,
Now, because this regard,
Yeah.
I mean, like, you have
to
more
read,
grace.
continued to put down the
so
stairs.
it's not
I know it's
sides and.
Yeah, so they came to our house and they
Okay,
said-
folks, it's 9:30, so gentlemen, hello.
Gonna get started now.
Yeah, we're starting. So, last week was difficult. I predicted it would be, and it always is. The topic we covered last week of astronauts experiencing life near a large gravitational mass is mind-bending. So today,
That's a
we're.
pun.
Yeah. In many ways, yeah, that's right, Bob is right. But today we're gonna come back down kind of to earth, or at least our neighborhood, and talk about the technologies that are used to measure the cosmos. And these are myriad in type, which is good, because astronomers of different, with different areas of attention gather together information that leads to what we have already talked about in here, the concordance of data collected from independent studies. And things can tend to come into focus because we get complementary confirmation of various things. So today, a lot of technology. Before we start, last fall, Nobel Prize in Physics awarded to 3 people. Jim Peebles, who's at Princeton, has been there. He and John Wheeler in the early 60s were among the only well-respected astronomers or astrophysicists who were thinking about cosmology and exotic objects like neutron stars and black holes. So Peebles gets essentially a Lifetime Achievement Award, and then Mayor and Coulot's for planet finding. So there's a little caricature. This is Jim Peebles. Ambitious people from this group who want to have something big to chew on can look at Jim Peebles' book called Physical Cosmology, much of which is just text. I mean, anybody can read it. It has interludes where there's some math, but it's not that common. It's a book now about 35 years old, but it really covers the whole landscape. And you can probably find a used version cheap. So that's something to think about. So the other two guys are from Switzerland and figured out how to use Doppler shift to detect planets in other solar systems. And their scheme is, if there's a solar system and most solar systems we think have sort of a planarity to them. They look like a rotating plate, like our solar system. We have a few oddballs like Pluto, which has a kind of weird inclined orbit. But most solar systems form by accretion of matter around a star, and the motion of those planets actually moves the star. The star and the planets are in this celestial dance. I'll show you what this looks like in a second. So, for example, in our solar system, Saturn and Jupiter, the two biggest objects, are tugging on the sun. The influence of Earth tugging on the sun is trivial in comparison. And so what we see is, and so what the result is the star moves. And if the star moves, you can detect that motion away from you and towards you by looking at the spectrum, the fingerprint, or the handprint of the spectra produced by the star. It moves back and forth. And this is an example of what you would see if you were outside our solar system and were looking at the sun and didn't know there were planets here. This is a time history. It goes back to 1945, and these rings, it's a continuous line, shows the motion of the center of the sun under the influence of principally Jupiter and Saturn. So,
Don't click it.
Don't click it.
yeah, sorry, that was my fault. I locked you out.
Well, we all make
So,
mistakes.
if you look at the notes, you can see this in a little more detail, but the sun moves around, and that would be detectable if you were an extraterrestrial looking at our solar system. Now, it turns out the size of the motion of the sun under the influence of our planetary system is so small that the motion, these curves, are confined inside the sun. So the sun is moving. You have to have extraordinary instrumentation to detect this, and that's what this Nobel Prize was awarded for, building astronomical instruments able to detect the motion.
Question?
Yeah.
So, when they look at the spectrum up from the sun or from a star, they're looking for very slight shifts toward infrared or ultraviolet.
Toward and away.
Right.
Right, so yes, blue shift and red shift. Well, actually, here it is.
What does limb of the sun mean?
So on here is the nucleus of the sun, which is where the thermonuclear fusion is going on. The limb is the thing we see.
Okay.
It's the glowing ball. So this is actually data from these two guys where you see the velocity. This is velocity over time measured, that's a week. And you can see a star, this is the Pegasus 51 Peg, I think it is, has planets, and so the star actually moves toward and away from us. Now, if you happen to be in a situation where the disk of that solar system is oriented this way, you don't see Doppler shift from that. You have to use another scheme to detect planets, and we will talk about that this morning.
What's the vertical scale?
This is velocity in meters per second. Notice these error bars, these little red dots, each have a little tiny line indicating the error. This is on the scale of measuring, not quite, but almost as good as what the police have if they're out on the highway with a laser measuring your speed or radar.
Is there a practical consequence of this discovery, the Doppler?
Well, all the you could say is practical includes science. Yes, and the answer is yes. I mean, the same Doppler shift that these guys exploit with exquisite precision is what Hubble used to detect the motion of galaxies away from our galaxy. So yeah, there's a long history of looking at spectra in distant stars. And this is a invention that lets us figure out not only that there are planets because of this periodic motion, but you can also tease out the mass of the planets. There's all sorts of science. And now, as it points out here, there's thousands and thousands of exoplanets have been found, most of them using this technique. There's another technique we'll talk about this morning. So ground telescopes are the foundation for what we know about the cosmos. So I thought we would talk about the technology and its evolution. So here is a highly nonlinear graph. So this is the size of telescopes in centimeters. There's 1 centimeter, and there's 10 and 100. So this is a logarithmic scale starting in 1600. So you go way back, and you have Galileo and so forth. And now we're up to 10 meters is a kind of a conventional size. And we'll talk about how you can build a telescope quite a bit bigger than this room. So here's a scale model. We have some references. Here's a basketball court. Hubble, the Hubble Space Telescope is right here. Hubble is 2.4 meter primary mirror. Remember, virtually all astronomy today is done with mirror telescopes, not lenses. So we should talk about that for a second. The early days, if we go back here, the early days, probably up to about right in here, all these telescopes were done using lenses. And there are several problems with lenses. The bigger you make them, the more massive they become, kind of as the cube of the diameter. And bigger is better in astronomy. We'll talk about why in a few minutes. The other problem is something called chromatic aberration. That is, light going through glass, light of different colors, focuses in different places because different colors interact with the glass in different ways. I'm right in the midst right now of finalizing a book on optical engineering, and a big section of the book is about aberration control and imaging. Yes, sir?
Your own lens in your eye has chromatic aberration.
Absolutely.
And you have a big dilated pupil, you bring out all of the rays to the periphery of your own lens, and it screws up your vision.
Right. So yes, this is absolutely true. So glass, because the properties of glass called the index of refraction is different for different wavelengths, different colors focus at different points, and it's a big challenge to deal with that in optical systems. The astronomers, as I say, maybe 120 years ago, decided, let's use mirrors to reflect the light, and then you immediately get rid of chromatic aberration. There are other issues, but anyway, you can see the scale of what we're dealing with here. So we have Hubble here, 10 feet in diameter, and unique, of course, because it's a big optic in orbit, and it's designed to be very stiff. So it's a piece of glass 10 feet in diameter and about 8 or 9 inches thick, with light weighting by machining the back of the mirror, remove as much mass as you can so you can actually lift this thing in orbit. It's a big challenge. New technologies are coming along, which we'll talk about. Another category of, so I want to point also here, Hubble is what is called a monolith. It's a single piece of glass, machined with extraordinary precision, and as some of you may remember, that the first pictures taken with Hubble were terrible, because it was perfect, and I mean perfect, except for one of the many aberrations that opticians talk about. It had something called spherical aberration. Because of the way it was tested, Congress was reluctant to pay for a special test facility when the Hubble mirror was being manufactured. So they did it in segments or in a sequence of tests instead of doing everything from end to end through the telescope. And they missed a little tiny, and I mean tiny, a defect in the shape of the mirror, measured on the scale of, let's say, 1/10 of the diameter of a human hair. And the genius scientist who diagnosed the problem, Chris Burroughs, was able to, when they got bad pictures, he diagnosed the pictures and was able to take control of the telescope for a short time to do experiments to figure out what was the problem, why are the pictures so bad. And he actually was able to diagnose exactly which defect caused the poor imaging. And then the geniuses at Ball Aerospace in Boulder built a thing that looks like kind of like a telephone booth. And the first time they had a chance to do astronaut servicing mission, they took out an instrument and put in this telephone booth called CoStar. And CoStar works like this. It was folded up when it was launched, so it would, like not too different in size from a telephone booth. Once in orbit, it went like this. It has mechanism, and then imagine little mirrors on the tips of my fingers. So it has a mechanism, and the mirror there are two mirrors that are on the tips of my thumbs. So light coming from the sky was intercepted by these two mirrors before it got to the science instruments. And these mirrors were designed to be defective in just the right way to correct for the Hubble defect. An extraordinary achievement, and I joined Ball Aerospace in 1993, and almost the first thing that happened was that NASA had a press conference at Goddard Space Flight, or maybe NASA headquarters, a big auditorium, and they had a whole array of people there celebrating the first really good pictures that they got after the astronauts installed this instrument. And there's nobody on the stage from the company that built the corrective optics. Nobody mentioned them except a guy named Jim Crocker, who said, you know, there's somebody missing here. And the Ball people built the instrument that fixed this thing, and now we're really getting good pictures. Now, subsequently, all of Hubble's instruments were built with a defect to correct for the mirror. The mirror itself has not been fixed, cannot be fixed. And a sad day is coming probably in 2023 when Hubble will be disposed of. In any case, back to our story, we have some big mirrors here, or some big telescopes here. The Keck telescopes, I'll show you more about them later. And notice these look like a mosaic, and that's what they are. I'll show you details. They are not monoliths. These are 10 meters in diameter, and when they were built in the mid-90s, the idea of building a 10-meter primary mirror for a ground-based astronomical telescope was just out of the question. So Jerry Nelson, another genius, figured out how to do this where you have segments, each about the size of a patio table, all actuated and controlled by computers so that when you put this thing together, everybody stands in the right place in just the right way. Even when the telescope is tracking across the sky, you know, if an exposure takes hours, everything is changing on a scale that matters for telescopes because their gravity is pulling on everything, and the parts of the telescope sag in minute ways, but it matters. So the computer keeps track of that. we'll get into some of that. And we have this bad boy, the European Extremely Large Telescope. Also, and now, so ginormous that you can't possibly build a single monolithic piece. The other thing is there's cost savings doing this. Because this is sort of a cylindrically symmetric, the outer row of mirrors can be made exactly the same, like the outer 3 rings. Then the next 3 rings are made the same, but they're different than the outer ring. But you can go into mass production of small pieces. So,
Are each of those little hexagons flat?
oh, no.
So they have curvature of their own?
Right. You would have a not very good imaging if you took flat pieces and even if they had overall the right shape, each of these pieces has to be computer manufactured and polished and coated. Yes, sir.
Why are they hexagons?
It's a convenient shape for making something approximating a circle. You can fill a circle with hexagons. Now, as you can see here, it's kind of rough around the edges, but that's not, most of these mirrors here are used for diagnostics anyway. They're not doing science with those.
Why aren't octagons better?
You could use octagons. It costs more.
No, there would be gaps. They don't mesh perfectly.
Well,
Hexagons do.
Well, you can make octagon, well, yeah, I don't know. There are manufacturing issues as well. So Ansel probably is on the right track. The Giant Magellan Telescope is, I think, commissioning this year. Now, it has multiple, as you can see here, multiple monolithic mirrors. And over here, this guy, the James Webb Space Telescope, is a deployed space telescope that hopefully is going to launch in 2022. This thing's been under construction since, I don't know, 1998. Maybe the first major contracts were maybe a little later, 2002. So we're talking about 20 years of building this thing. Multi-billion-dollar facility. And we'll also talk about that today. So anyway, this is a handy picture for showing the difference that we have in the way telescopes are done, monolithic or segmented, and single aperture or multiple aperture. For example, this very large telescope, which I will talk about at length because I worked on it, is multiple telescopes that can be used together in synchrony to produce the equivalent of a larger telescope. So here's another way to look at this, again from 1600, and we see the names of the various telescopes, and we're making a distinction here between reflecting telescopes, that is, ones that use mirror technology, and refractive telescopes, the ones that use glass. And you'll see there are some reflectors here. One kind of cute way to do this is to have a tub of mercury and it's rotated. And the mercury will kind of climb the walls of the tub. Now you can only do this looking vertically, so you have to have additional optics if you want to be able to look at different places on the sky. And there's a little bit of activity in that field. The Canadians actually are a world leader in these kinds of rotating mercury things, because they're very cheap to build. You just need a mechanism to rotate and a pile of mercury. So, the telescope itself that collects the starlight has virtually no glass in it. It's all mirrors, and in fact, an interesting way to think about this is like the Hubble I mentioned. The mirror in the Hubble weighs tons, and it's a glass thing this thick. It's made of Pyrex, kind of like the stuff you use in your kitchen, because it has good thermal properties. But the actual business of reflecting the light is all due to a microscopically thin layer of metal that's on the face of the mirror. But the mirror